All right, people, our mission is to get through this const expression function section and references and pointers in an hour. Um, we're trying to go through Learn C++. I've taken more thorough notes on std vector, but I think it wouldn't hurt to review these and have a better understanding. But we got to start earlier on in order to do that. So, all right, we are going to start. I'm also going to be taking notes, but I'm not going to show my iPad. It's a little loud for me. Also introduce constant expressions, which are expressions evaluated at compile rather than runtime. One challenge with constant expressions is that a function call to a normal function are not allowed in constant expressions. This means we cannot use such function calls anywhere where a constant expression is required. Okay. Sure. Makes sense. Having a complex initializer for circumference. Double. Sure. It also doesn't compile. Constant expression. Circumference is trying to get return from this. But the function isn't constant expression. There are other cases in C++ where we'll introduce. Okay, anyways. Constant expression functions can be used in constant expressions. I think that might be the first thing to note. Let me jot this down. Oh, it's also... Oh! Let's also make this... Cool. Okay, we want to mark this down. Constant expression is to eval at compile time rather than runtime. That was weird. Anyways. Okay. Constant expression functions. Can be used in constant expressions. So my first thought is, does this work the other way? Meaning, if we have this, but we go visual and then AL. Trying to get better at those commands. Does this work the same way? G++ -C++ 17. Okay, so it can be evaluated, but it doesn't have to be. So that can be used as actually very useful information. Constant expression functions can be evaluated at compile time. Yeah, that makes sense. I'm assuming you have to have everything in there being constant expressions. Know that contexts require constant expression. Constant expression is required to evaluate at compile time. In our example above, when a function call is evaluated at compile time. The compiler will calculate the result and return. Okay, makes sense. Compile time. Two other things must be true. This is important. To eval at compile time. Two other truths. Two conditions. What would the other one need to be? To evaluate, I'm not looking at the screen, but passing in those must be const expression. That makes sense. Is that anything within the function also has to be? All statements and expressions within the function must be evaluatable at compile time. Yep. Okay. Everything in the function must be Const expression can also be evaluated at runtime. In the case, they return a non-const result. Yeah, so it can go the other way. Const expr function can return runtime result if assignment is not const expression. Part 2. I expect that a const expression function would evaluate at compile time whenever possible. That's not the case. We noted that in contexts that do not require a constant expression, the compiler may choose to evaluate. Yeah, this makes sense to me. Diagnosis of const expression functions in required const expressions. The compiler is not required to determine whether, okay, makes sense. It's fairly easy to write a const expression function that compiles successfully for runtime use, but then fails to compile when evaluated at compile time. A silly example. Get value. Oh, you're acquiring on get value. Let's run this. Fail case.cpp. So my thinking is foo of 5 get value. And we're just returning. But this isn't a const expression. I'm thinking this is fine for X, but it's not fine for Y. Makes sense. Get value can't be evaluated. Okay. Are implicitly inline. That's good to note. Another example. Let's do another example. This will return a const expression. I can see this being either. Oh, it says it there. Not const expression. Runtime. Runtime. Got it. Oh, okay. C++20 feature. called immediate functions. Okay, so an immediate function is one that's const evaluated. Using const eval to make const expression execute at compile time. Oh, they can't evaluate at runtime. Okay. Let's jump to the summary. Ah, damn it. Const eval functions can use non-const local variables. Oh, so it'll just execute this whole thing. Interesting. Const expression, use function parameters. And local variables as arguments. This makes sense. Can a const expression function also call a non-const? Oh. Only one. Okay. So it can't be const eval. Advise following. Avoid calling non-const expression functions with const expression function if possible. Okay. Always test. Yeah. Unless you have a specific reason not to. A function that can be evaluated as far as a const expression should be a const expression. Right, you can't breakpoint and get an iTrace. Alright. Let's do the summary. Const expression is a function that is allowed to be called in a constant expression. To make a function a Constexpr function, we simply add the keyword in front of the return type. These functions are only guaranteed to be evaluated at compile time with two conditions. The function must have args that are known at compile time, and everything in the function must be valuable at compile time. They're implicitly inline, and the compiler must see the full definition of the function to call it at compile time. Const eval function must evaluate at compile time, breaks otherwise. Okay. Let's look at this quiz. Okay. Add a const or const expression to the following program. That is vague. Okay, so in our main, we're calling print calculated ball height. First we have a double, which is tower height. So my first thinking, let's look at this get tower height function. This get tower height function doesn't have anything in here that enter the height. Oh, it has C in. So this cannot be const expr because has to be done at runtime due to cin. Okay. So that'll return whatever height we put into the system. Print calculate ball height gives us our tower height, which isn't a constant expression. I don't know how any of this could be. Okay, well, let's look. This one, I definitely can see why it would be a const expr. I just think, I think we're good with this. So print calculated ball height does so this is a const, obviously we're not changing gravity. And our tower height isn't going to change either. And then we're printing. Okay, let's see if this compiles. Seconds is not a constant expression. But tower height is? Hang on. Wait. In what function? In print calculated ball height. Const expr. Seconds is not a constant expression. I don't fully understand what they want. Right? That one can't be. I can see why this one can, but okay, let's get rid of this. Oh. Oh, that's down. Still learning Vim to some degree. PH? Nope. PK? Nope. Let's just can see why these would be double or consts. We can't do anything in the print, right? Const double. And then make this a const as well. .62.9. Okay. So even though we have a function that is going to be at runtime, we can still have everything else essentially be an inline compiled macro at compile time. That makes sense. All right. Compound data types. C++ supports a second set of data types, compound, composite data types. So is this like our structs, our class, our unions? The following compound types: functions, C-style arrays, pointer types, pointers to members, reference types, enumerated types, class types. I'm using one compound type regularly, functions. So this is compound because we're taking an int and a double. A class type is a type that is a struct, class, or union. Okay. One of the biggest pitfalls in C++, L values and R values. Okay. Value categories. All right. We're talking about our first. 2 plus 3 is evaluated to produce 5. Now that expressions can produce side effects that outlive the expression. Sure. Type of an expression is equivalent to the type of the value, object, or function that results from the evaluated expression. The type of an expression Okay. Interesting. Okay. For v1, both are ints. What is... const expr. Let's make chapter 11 or 12. Refs and pointers. I thought I made that already. Okay, anyways. Wait, for real? Oh. Okay, so what if we do like 4.1? Okay. Got it. Okay. 5 equals x is not. L is literal. Okay. The value category. An expression. Indicates if resolve to value function or object. Alright, let's look at these value categories. Alright, let's start with those two, and then we'll just mark down that there's also these two after, or these three after C++ 11. Okay. How did I not take notes on this before? So for full transparency, I probably got to chapter 18 and then I was going through some Learn C++ quizzes questions, and I was like, oh, I've already covered this, and I don't know the answer. So I'm taking notes. Okay. Okay. An R value is an expression that is not an L value. So true. Eval to a value. In x5, 5 is the R value. Okay. Cool. Since assignment operations expect the right operand to be an R value expression, is there a temporary value involved here? In cases where R value is expected but an L value is provided, the L value will undergo L to R value conversion, so it can be used in such contexts. Assignment is L value equals R value. If L value equals L value, convert to R value. Okay. Okay. Let's jot down this tip. L value expressions are those that evaluate to functions or identifiable objects. That persists beyond the end of the expression. R value expressions evaluate to values. A C-string literal is an L value because C-style strings are a pointer. Decay to a pointer, that is. That makes sense. All right. In C++, a reference is an alias for an existing object. L value references. This is important. In C++, a reference is an alias for an existing object. Once a reference has been defined, any operation on the reference is applied to the object being referenced. Alright, so we can pass references into a function and modify those in place without creating like a copy or whatever. Makes sense? Though references might seem silly, that's crazy. Reference types. Int and L value you reference to int object. There are two kind of L value references. An L value reference to a non-const. L reference to const, or const L value reference. Okay. L value reference variables. One of the things we can do is create L value ref. Yep. And then, so let's just do them lval ref.cpp. Let's do this, and then let's change. I gotta change my spacing. How many spaces? That's 4 spaces. Ref equals 6. I'm expecting both of these to change. Whoops. Yep. Non-const L value ref. Yep. We just did that in the example. Reference initialization. We say it is bound to that object or function. Process by which. Okay, that's important. is initialized with an object, we say it is bound. The process by which such a reference is bound is called a reference binding. The object or function being referenced is sometimes called the referent. Love that movie. Non-constant value references can be bound, but can only be bound to a modifiable L value. Interesting. So if we have const ref.cpp, I gotta ingrain a macro for the compilation. Okay, but what if we do const int? And then if this is a const, like I get it. Because const is read-only, we don't want a reference that is an alias that could possibly change the value that we're looking at. I completely get that. Reference scope, they can have independent lifetimes. Oh yeah, that makes sense. Dangling references. Perhaps surprisingly, references are not objects in C. Nope, that's the wrong section. When an object being referenced is destroyed before a reference to it, the reference is left referencing object that no longer exists. Leads to UB. Okay. Quiz time. Determine what values in the program print by your do not compile the program. Well, I'm just going to add it here, but lref q1.cpp. Okay. So we have x equals 1. 1 is an R value, x is an L value. Ref is bound via reference binding to x. These will both output as 1. So this will be 1, 1, new line. Now we have a new L value called y with an assigned to an R value of 2. And now ref is bound to y. Now y is updated to 3. If this is a reference to x, first thing is, does this get reassigned or overwrite value? My intuition is telling me because the ref, that assignment will boil down to an L value equals R value. So y will become 2 as an R value, and now x will equal 2. With y equaling 3 here, I don't think that changes anything. So I think it will be 1, 1, and I think it will be 2, 2. And now x equals 4, I think this will be 4, 4. I don't think y equals 3 has anything to do with it because I don't think it relinks. So C++ 17, we're expecting 1, 1, 2, 2, 4, 4. Yep. So now we for sure know this overwrites value. Cool. L value references to const. I think I already did. Oh. Oh, unless you need to. Okay. Int main short const int u. You can has bomb too. Oh, it's an int though. Bomb all gone. You still has? Oh, it's not modifiable. Const reference is bound to temp objects. Extend the lifetime of the temp object. Fair enough. That makes sense. Pass by L value reference. Yeah, so it's copied. Right. I do remember reading through this section. Pretty much you want to use a pass by reference to avoid making copies of stuff because that's memory overhead in the stack, which isn't necessary if you're modifying it in place. Okay. So pass by L value reference. Some objects are expensive to copy. Pass by reference, we can ref doesn't copy. Copy direct alias. Yep. Pass by const. Right, we can't modify these, obviously. Best practice, as a rule of thumb, pass fundamental types by value, class types by constant. Okay. Introduction to pointers. Pointers are one of the C++. I love pointers. Okay. I think, my bad. I think I've been breathing in the mic this entire time. Pointer is an object that holds a memory address. This allows us to store address of some other object to use later. Declaring a pointer type, place an asterisk next to the type name. Yep, that's how I use them too. That's a very good diagram. We have our pointer. When we dereference it, it has this value. Pointer's an assignment. We can use assignment to change what the pointer is pointing to. We just reassign pointer. Yep. Dangling pointers, obviously bad. Let's just quickly write that. Dangling pointer. Pointer. Points to address of an object that is no longer valid. Okay. Quiz time. What values does this program print? Assume short is 2 bytes and a 32-bit machine. Okay. Okay. Those pointers are the same, so I think that's fine. We get this address, we get 7. We get pointer, we get this address. If we get dereference pointer, we get 7. Now we update the value at the pointer to 9. The address won't change. The value will now be 9. Address won't change. Value will be 9. Now we reassign the address of the pointer to 3. Our other value, which points to 3. Our other value is the object that holds 3 in it. Okay. Will be this address. Other value will be 3. Pointer will be the same address as other value, and that value will be 3. Yep, 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 yep. Sounds about right. What is wrong with the code snippet? That's fine. That's valid. We're dereferencing and then assigning to a pointer. Yeah. Null pointers. Cool. Dereferencing a null pointer is UB. Okay. Pointer should either hold the address of valid object or be set to null pointer. Yep. So you don't access random memory. You want to get the dereference. Ha ha ha. Can we determine whether a pointer is a null pointer or not? Yes. You do the assignment equals null pointer. Can we determine whether a non-null pointer is a valid or dangling? If so, how? If a non-null pointer is dangling, how could we do this? So it's obviously, if it's dangling, it's referencing something that has left scope and it's been destroyed. I don't think we can. Okay. For each sub-item, answer whether the action described will result in behavior that is predictable, undefined, or possibly undefined. If the answer is possibly undefined, clarify when. Assume that any objects mentioned are a type that the pointer can point to. Assigning the address of an object to a non-const pointer. Predictable. Assigning null pointer to a pointer. Predictable. Dereferencing a pointer to a valid object. Predictable. Dereferencing a dangling pointer. That is UB. Dereferencing a null pointer. Also UB. This is possibly undefined if it's dangling. To a T. To a fucking T. Wow, look at that. Why should we set pointers that aren't pointing to a valid object to null pointer to make sure they're not pointing to gross or random memory that is being used otherwise? Pointers and const, we're using const pointers. I get pass by. How much more do we have? Pass by address. Type deduction. This is actually useful. Give me 1 second. I'll be right back. All right. Let's keep going. Passing by address. Right, so in this case, we have copy overhead with the address. So assuming a 64-bit system, that's 8 bytes. But if we're passing in, I really don't know the use case of where we're using a pass by pointer versus a pass by reference. To me, they feel the same in terms of their efficacy for the most part. Okay. Use pass by address. We made our function parameter pointer. Pass by address does not make a copy of the object. Pointer to const function parameters over pointer to non-const. That's not good. Prefer pass by reference. To pass by a DDR. So, kind of want to go to chat for something. What's the use case for pass by pointer versus pass by reference? In C++. Yeah. And the argument is optional. The function may reassign the pointer itself. Oh, okay. So it was fairly useful with the ring buffer I made. Okay. All right. So you have a default. You have a default argument. Oh, okay. Can be used to update address and provide optional arg if null pointer. pass by address by pointers by reference. That's funny. There's only one pass by value. Return by reference and return by address. Which avoids making a copy of the return value. Right, do we need to make this static? Hang on. Okay. Warning, reference to local variables. See, that's what I was testing. Is this is going to be a dangling reference. So we need to make it static. Makes sense. Turn by ref object must exist after function returns. Yep. Lifetime extension doesn't work across function boundaries. Okay. Lifetime extension doesn't work across function boundaries. Let's take a look. Right, this is dangling. Don't return, yeah. Here's another example with less obvious version of the same problem. Okay, get name and get name. My thinking is they're never references initialized to begin with. returns a reference to a static local S name, initializing a const string reference with a reference to S name. Cause it. Oh. Return by address. So yeah, these can both dangle. That not good. In and out. Oh, so out parameters you pass by either reference or address and you update them. I was doing this a lot at work. Function parameter, yep. Out parameters has unnatural usage syntax. Not really. Even if it doesn't intend to use it. That is true. To be obvious. Avoid out parameters. Well, okay. So, I disagree with this to one main factor. In Python, you're able to return multiple objects with one return statement, right? C++, I believe the only way to do that is if you use a pass by reference or pass by address and update it that way. So that part, type detection of pointers. Okay, this is the one I wanted to really read. Okay. Deduced as int. Gosh, C++ really dropped auto just to add interview questions into the pool. Right, const is dropped. Type deduction drops references. What does that mean? Oh, I know what that means. top level const and low level const. This const applies to the object being referenced, so it's local. Okay, type deduction. If the initializer is a reference to const, the reference is dropped first, and then okay. And any top level is dropped, but low level doesn't? Unlike references, type deduction does not drop pointers. Interesting. Okay, cool. Top level. Makes sense. When we're referencing the object with const, it's top level. Low level is when the pointer in reference is const. Okay. The type deduction deduces, drops any references, then drops any top level const. Const expression is not part of the type system, so it's never reduced. Does not drop pointers. When using auto, the deduced type will be a pointer only. Okay. STD optional. So I'm assuming optional just indicates that like there's a chance we're not returning a value. C++ 17. Indicates chance we return nothing. Cool. Alright, we are at the summary and quiz. Compound data types, yep, can be functions, can be struct types, or class types, can be a lot of things. Value category can either be, well, there's 5 in total, but we only covered 2. L value is an expression to an object or a function, and R value is a literal or anything that's not an L value. A reference is an alias to an existing object, while a pointer is an actual address to a given object. When a reference is initialized, we say it's bound using reference binding. Once initialized, a reference in C++ cannot be reseeded, meaning it cannot be changed to another reference or object. That's hence the R value translation we were seeing in that quiz. When using a pass by reference, we have to declare it first and then pass it through. Address of operator gives us the address of an object, and the dereference pointer gives us the value at that given address. A pointer holds a memory address. Pointers are not a pointer that has not been initialized is called a wild pointer. A dangling pointer is where we're referencing an object that just came out of scope or got destroyed. A pointer to a const value, pointer to const, is a non-const pointer that points to constant value. A const pointer is a pointer whose address cannot be changed after initialization. Const pointer to a const value, neither can change. Pass by address and pass by reference, or return by address and return by reference. Okay. For each of the following expressions, on the right side of the operator, indicate whether the expression is an L value or an R value. std out 5, that is an R value. X is an L value, 5 is the R value. Plus 1, this is an R value. Int foo, I think this is an L value. Return function, which is returned by value, is an R value. Okay, that's good to know. So returning by value, that will result in an R value. Okay. Reference, max, takes in 2 references, returns. Okay. So those will stay in scope. We have X is that, Y is that. Max of these 2. It's a reference. It has to be an L value. Bang. What is the output of this program? We have X initialized to 4, Y initialized to 6, reference bound to X. We pre-increment the reference, so now, well, okay, so X equals 5, then X equals 6, then X equals 7. So X is 7, this is, and Y is 6. Q1.cpp. Copy it. There we go. Seven, 6. What I say. Name 2 reasons why we prefer to pass arguments by const reference instead of by non-const reference pointer. Or non-const reference, not reference pointer, whenever possible. We can safely say that for sanity, that we're not modifying anything if we pass by const reference. But if we pass by non-const reference, we can modify the value. Can only accept the modifiable value. Oh, it can take anything. That's good. That's good to know. So a const reference can also take both types, but a non-const reference can't take a const. What's the difference between a const pointer and a pointer to const? A const pointer, the address can never be changed because the address itself is read-only. And a pointer to const, the address can change, but the value at the address you're initially pointed to before the change cannot be changed. Write a function named sort2. Okay. Write a function named sort2 which allows the caller to pass two int variables as arguments. When the function returns, the first argument should hold the lesser of the two values, and the second argument should hold the greater of the two values. Okay. Chapter 12, q2.cpp. Void sort2 of int x, comma, int y. We could also get really fancy and do this with templates. Okay. Anyways, we want the function returns the first argument should hold the lesser of the two. Okay, so if x is greater than y, int star temp equals the address of x, the address of x equals the address of y, and the address of y equals temp. Whoops. L value required. Wait, what? This should be so easy. I'm confused. Is this not what we usually do? How would we make these? Because this... They don't want the addresses swapping, they want the values swapping. Ahaha. Ooh. Saw that typo? What am I doing? Wait, what? Hang on. I don't want to use swap. But it's by reference. Do this with pass by. I see the issue. Yeah, so that was stupid on my part. Took me long enough to figure that out. Jeez Louise. Cool. I think now let's do a quick chat quiz. I just went over const exprs. Wait, no. Nice, concept what the trickier concept. And chapter 12 in Learn C++. Do you know what content is in chapter 12? No, it's not. It's covering refs and pointers. You're lying. Jeez, I guess it doesn't know. What is the main difference between constant expression and a regular function? Constant expression is evaluated at compile time, if possible. When a constant expression is evaluated at compile time versus runtime, if everything is known within a function, it's able to be evaluated at compile time, but if it has variables that can't, then it's evaluated at runtime, because it doesn't know. Why must all parameters and return values be literal types? Literal types are able to be evaluated at compile time, so they're not unknown. Can constant expression function contain an if statement or loop? Yes, it can, but all results have to be known to the compiler. What's the difference between constant expression and constant eval? Constant expression will compile or be done at compile time if possible, else it'll be done at runtime. Const eval requires compile time interpretation and will fail otherwise. What happens if a constant expression function cannot be evaluated at compile time? It will default to runtime. What is an L value versus an R value? L value is an object or function. An R value is something that isn't an L value. It's a direct value. Explain the difference between this reference and a constant int reference. Constant int reference prevents you from modifying the aliased object, whereas a reference, you can modify it. Can a non-const L value reference bind to a temporary value like 5? How many of these did it ask? Let's start at Q8 and go one at a time to Q20. In terms of what each allows, ref can modify value of x. Cref can't. It's as simple as that. Can a non-const... No, it can't. The assignment has to be an R value. Or, sorry, it has to be an L value. I'm not sure what kind can. An R value reference? Const can. Oh! Why did it... I'm gonna mark that down. R value ref. Int and ref equals 5. Cool. What is the value of x after this? 20. What's the output of this code? 10. This is stupid. Explain the difference between const int pointer and int star const pointer. Const int star makes the int const, not the pointer. Int star const makes the pointer const, not the int. Why is passing by const reference offer preferred? We just went over this. So passing by const reference, const ref can be used for const or non-const params with added safety of no modification. That's part of it. Oh, and copying. What's the difference between pass by address and pass by reference? Address gets passed in versus the alias. Pass by address can be null, usually used for optional params, whereas pass by reference has to refer to an L value. Why must you be careful returning by reference or by pointer from a function? Dangling. What does optional do? You can indicate that something might not return from the function. Given this function, in reference get element returning a vector of the index. Why is returning by reference useful here? Why would it be super useful here? I get for the vector. Can modify in place. Yeesh, this is slow. Oh my gosh. That's crazy slow. Hang on. Let's just get the other questions. What is this output and Y? Points to A. Then we reassign the pointer to B. A is 5, B is 20. If you have this, what's the type deduction? Y is int. $19 would be useful. Why can't a reference be reseated, but a pointer can? I don't know why it can't under the hood. That's actually a good point. So this would be 5 and 20. Y is int reference. Z is const int reference. That was a stupid question. Why can't a reference be reseated but a pointer can? Reference after initialization only takes R value assignments. Pointer can be addressed to L value. Becomes an alias for the entire lifetime. Okay. All right, y'all. I gotta cut it here. I need to get down to campus, do some drone work. All right, bye.